We are starting our unit on parametric equations and polar equations. So in this first section, we're going to be reminding ourselves what parametric equations look like, and we're going to be finding dy dx, the slope of the tangent line to a curve, and the second derivative of y with respect to x, which will describe the concavity of the curve, given x of t and y of t parametric equations. So let's remember what parametric equations are. A set of parametric equations describe a single curve with two equations. We have one equation for the x component and one equation for the y component. Together they create a curve. And these curves they don't have to be functions. They don't have to pass the vertical line test. So it is convenient to think of t as time. So at any time, we can find the x coordinate of the position and the y coordinate of the position. It makes sense that we can draw tangent lines to the curve at various points. And if we can draw a tangent line, we should be able to determine the slope of the tangent line, which is dy dx. So we are going to be able to find the slope of the tangent line at any point on the curve that we like. Okay? It also makes sense that this curve has concavity and that we should be able to find out something about the concavity of the curve. So on this curve, on this section, the curve is concave up. Yeah? But at some point, the curve becomes concave down. Yeah? So if this curve starts here, I don't know, it might go like this and wrap around and then come back and start repeating itself. In general, these guys with trig functions, they oftentimes repeat themselves after a certain time, after a certain t value. So that's what we're going to be doing. We're going to be finding, in this section, we're going to be finding the slope of the tangent line, and we're going to be finding out, we'll be able to determine the concavity of the curve. Let's look at some examples. Let's say that we are given the parametric equations x is equal to square root of t and y is equal to 3t squared minus 2t. If I want to find the slope of the tangent line, I know that that is dy dx, the derivative of y with respect to x. Well, we have dy dx, we need dy dx. We have x and y as functions of t. The differential of y over the differential of x is dy dt over dx dt. The notation, Leibniz's notation, makes a lot of sense, because if we did multiply top and bottom by dt, we would get dy dx, right? dy over dx. So dy dt is 6t minus 2. dx dt is, I'm thinking of this as 2t to the 1/2. So 1/2 times 2 is 1. Decrease your power by 1, and we'll have t to the negative 1/2. This, of course, would be a safe stop. And if this was the only thing I was being asked, I would definitely just stop there, call it a day. If it was multiple choice, that would not be the choice. So we would have to mess around with it. I would multiply top and bottom by t to the 1/2 to get this bottom to be a 1. And so this would be 6t times t to the 1/2 will be 6t to the 3/2 minus 2t to the 1/2. So I can see that being a multiple choice answer. Part B. Now we're asked to find the second derivative of y with respect to x. Well, the second derivative of y with respect to x is the derivative of the first derivative of y with respect to x with respect to x. So this is the derivative with respect to x of dy dx. We just found dy dx. So we are taking the derivative with respect to x of 6t to the 3/2 minus 2t to the 1/2. If you're finding the second derivative, always simplify the first derivative. Always simplify it before you find the second derivative. You'll be helping yourself if you do. You will get a complete mess sometimes if you don't simplify before finding the second derivative. So now take a look at what we have. We're taking the derivative with respect to x of something with t's in it. So we have to do implicit differentiation. Implicit differentiation. So I'm going to begin by taking the derivative with respect to t, then I'm going to multiply by dt dx. So first the derivative with respect to t. Little power rule here, 3/2 times 6 is 9. T to the, reduce the power by 1, minus 1/2 times 2 is 1. T to the, decrease the power by 1. That's the derivative with respect to t, and now we multiply by dt dx. Well, we don't know what dt dx is, but we do know what dx dt is. So I can change dt dx to the reciprocal of something I do know, dx dt. dt dx is 1 over dx dt. So now we have 9t to the 1/2 minus t to the negative 1/2 divided by dx dt. And we know what dx dt is. We found it up here. dx dt is t to the negative 1/2. So that is the second derivative in terms of t. That would not be a multiple choice answer. They would not ever leave it like that. They would multiply top and bottom by t to the 1/2 again. And this would be 9t to the 1/2 times t to the 1/2 is 9t minus t to the negative 1/2 times t to the positive 1/2 is t to the 0, which is 1, all over 1. So this would be the multiple choice answer. Okay? A very common mistake I see students make is when they find the second derivative, all they do is take the derivative of the first derivative with respect to t. They just get this 9t to the 1/2 minus t to the negative 1/2 part. They fail to multiply by dt dx. They're taking the derivative of the first derivative not with respect to x, but with respect to t. And that's not true. That's not what this is. So don't fall into that trap. Okay? Number 2. Given this set of parametric equations, we have x is equal to 4 cosine t, y is equal to 3 sine t. Write an equation of the tangent line. Write an equation of the tangent line to the curve at the point where t is 3 pi over 4. Equation of the tangent line, I know I need point and slope. And then I can get the equation. Right? So let's first do the point. For our point, the point will be xy where time is 3 pi over 4. So I need to find x at 3 pi over 4 and y at 3 pi over 4. Well, x at 3 pi over 4 is 4 cosine of 3 pi over 4. Cosine of 3 pi over 4 is a negative square root of 2 over 2. It's over there in the second quadrant. So that is negative 2 square root of 2. Y at 3 pi over 4 is 3 sine of 3 pi over 4. Sine of 3 pi over 4 is square root of 2 over 2, positive in the second quadrant for sine. So this is 3 square root of 2 over 2. Now it's time to do the slope. We got the x and the y coordinates of the point. For the slope, I know slope is dy dx. That is dy dt over dx dt. And by the way, for notation purposes, if you prefer, you can call dy dt y prime at t and dx dt x prime at t. Either way is perfectly fine. I have no preference. You'll see that I use them both, so it doesn't matter to me. Y prime of t is 3 cosine t. X prime of t is negative 4 sine of t. And then we're going to plug in our point, x, dy dx at our time, 3 pi over 4 is 3 times cosine of 3 pi over 4 is negative square root of 2 over 2. Sine of 3 pi over 4 is positive square root of 2 over 2. The square root of 2 over 2's will cancel. My negatives cancel, and I have 3/4. So our equation is y minus the y coordinate of our point is equal to our slope times x minus the x coordinate of our point. So everything that we did with functions, we can do with parametrics. Number 3, a curve is described by these parametric equations. We have 3 things to do here. First of all, we're going to find the t-value or values where the curve has a horizontal tangent line. A horizontal tangent line. Well, a horizontal tangent line is where the slope is 0. And the slope is 0 when its numerator is 0. Yeah? So the numerator, dy dx is 0. I'll write this down here too. Dy dx is 0 when dy dt, the numerator, is 0. So dy dt is 2t minus 3. Set that equal to 0. T is 3/2. So that means that we have a horizontal tangent line when time is 3/2. And that's what we were asked to find, the t values. So t is 3/2. Next up, we're going to find the t values where the curve has a vertical tangent line. Well, vertical tangent line occurs when dy dx is undefined. And that is when the denominator is 0. So dy dx is undefined when dx dt, its denominator, dx dt, is 0. And dx dt is 2t plus 1. Set that equal to 0, and we get t is negative 1/2. That would be the time when we have a vertical tangent line, but they gave me that t has to be greater than or equal to 0. So, since t is greater than or equal to 0, this curve has no vertical tangent lines. Vertical tangent lines. Okay. Next up, let's determine the concavity of this curve for t greater than or equal to 0. Well, I know concavity. For concavity, I need the second derivative. So we're going to find the second derivative. Well, first we need to find the first derivative. So we need to find dy dx. That is y prime of t over x prime of t. dy dt over dx dt. Y prime is 2t minus 3. X prime is 2t plus 1. And we cannot simplify that, so I just leave it like that. And now we're going to find the second derivative of y with respect to x, which is the derivative with respect to x of the first derivative of y with respect to x, 2t minus 3 over 2t plus 1. So again, we're finding the derivative of this with respect to x. So first we're going to take the derivative with respect to t, then we'll multiply by dt dx. So with respect to t, I need to use the quotient rule. The derivative of the top is 2, multiplied by the bottom left alone, minus for the quotient rule. The derivative of the bottom is 2, multiplied by the top left alone, all divided by the bottom left alone, but squared. And all of that we multiply by dt dx. Well, once again, I don't know dt dx, but I know dx dt, so we're going to change dt dx to 1 over dx dt. In the process, I'm going to go ahead and simplify this numerator. I'm going to distribute, so I'm going to have 4t plus 2 minus 4t plus 6, all divided by 2t plus 1 squared, and I am multiplying that by 1 over dx dt, which is x prime of t. Yeah? In the numerator, the 4t's canceled out, and I'm left with 8 in the numerator over 2t plus 1 squared times x prime of t. X prime of t. Well, x prime of t is 2t plus 1, which is the same thing that I have squared there on the in the denominator. So that is 8 over 2t plus 1 cubed. All right, we were supposed to determine the concavity of this curve for time greater than or equal to 0. If I put a positive number in for t, the second derivative of y with respect to x will be positive. So when t is greater than or equal to 0, the second derivative is positive. Therefore, this curve is concave up when t is greater than or equal to 0. Nice, huh? I like it. Okay, number 4. The particle travels in the xy plane in such a way that dx dt is this and dy dt is that for time greater than or equal to 0. The particle is at the point ln of 3, 2 when time is 0. What is the position when time is 2? When time is 0, I know that x of 0 must be ln of 3, y of 0 must be 2. and I know the rate that x is changing and the rate that y is changing. This is screaming to me to use the fundamental theorem of calculus, FTC. X at time 2 minus x at time 0, change in x, is the integral 0 to 2 of x prime. Fundamental theorem. These are t values, x at t values, right? So, set up the fundamental theorem. They told me that x of 0 was ln of 3. And I can find this integral, that's 1 over t plus 2. So x of 2 minus ln of 3 is, the antiderivative of 1 over t plus 2 is ln absolute value t plus 2. We will evaluate that from 0 to 2. X of 2 minus ln 3 will be ln of 4 minus ln of 2. So x of 2 is ln of 4 minus ln of 2 plus ln of 3. That would be a safe stop spot when we're writing, if this was an FRQ, that would be a safe stop spot when we're writing our point. I still need to find y. That would be fine, but as a multiple choice question, that would not be how they write that. They would definitely use log properties. When you're adding logs, you multiply their arguments. When you're subtracting logs, you divide by their arguments. So that would be ln of 6. That's how they would write that answer. We're going to do the same process for y. So y of 2 minus y of 0 is the integral 0 to 2 of y prime. They told me y of 0 was 2. And they told me y prime was 4t. So we have y of 2 minus 2 is equal to, the antiderivative of 4t is 2t squared from 0 to 2. This is going to be 8 minus 0. So y of 2 is 10. So at time 2, the position is ln of 6, 10. I don't know why I boxed it, but I guess because I'm done with this set of notes. So that is our first day of parametrics and calculus.